Okay, not the second law. Okay, yes. Now, before starting or going to the second law, first we'll see what are the limitations of the first law. Before going to the second law, we will see what are the limitations of the first law. Okay. Now see here, let us take example of cup of coffee. Okay. A hot cup of coffee gets cooled off when exposed to surrounding, right? So energy lost by coffee is the energy gained by surrounding. So total energy content is conserved. So here first law of thermodynamics is satisfied. First law काय म्हणते, जर तुमची total energy जर conserve होत असेल तर मला काय देणं घेणं नाही. So according to me the system is okay. But here in this case, can you gather all that heat lost to the surrounding, energy lost to the surrounding, and put it back into the cup? Can you increase the temperature of cup of coffee by doing so? No. To increase the temperature of cup of coffee, again, we have to put it on gas and then we have to boil the coffee. We cannot again search for all the heat lost in the surrounding, gather it and put it back in the coffee. It is not possible. Okay. So first law does not give you direction. So by first law, you cannot get the direction. So here, converse is not true. That is taking out heat from surrounding, coffee getting hot. But first law will say it is possible because all the energy is conserved. पहिल्या केसमध्ये तुमची cup of coffee तून heat transfer झाली आणि ती थंड झाली. It is first law says okay, total energy is conserved, no problem from my side. Then I took the second case. Second case मध्ये मी सगळी एनर्जी बाहेरची गोळा केली, परत कॉफी मध्ये टाकली आणि कॉफी गरम झाली. ही हायपोथेटिकल केस आहे, इट इज नॉट अ रिअल केस. बट फर्स्ट लॉ काय म्हणते की टोटल एनर्जी कॉन्झर्व झाली सेकंड केस मध्ये, मला काय प्रॉब्लेम आहे. त्यामुळे फर्स्ट लॉ तुम्हाला सांगू शकत नाही की ती सिस्टीम और ती प्रोसेस खरंच फिजिकली पॉसिबल आहे की नाही. दॅट इज द लिमिटेशन ऑफ फर्स्ट लॉ. फर्स्ट लॉ ओनली चेक्स फॉर conservation of energy. It does not check the direction or the possibility of the process. So the first law is satisfied. Now we'll take second example, very common example. Okay, so you have a heater, electric heater in a house. Okay, when you heat the coil, it will transfer the heat to the surrounding. किंवा तुमच्या केस मध्ये घरी जर गीझर असेल तर गीझर मधलं तुम्ही काय करता, पाणी गरम करता इलेक्ट्रिक कॉइल. But if I take the other converse or the reverse of that reaction, सगळं गरम पाणी आहे, गरम पाणी त्याचं हीट तुमच्या कॉइलला ट्रान्सफर करेल आणि कॉइल मध्ये इलेक्ट्रिसिटी जनरेट होईल, असं होऊ शकतं का? तर नाही. द कॉन्व्हर्स इज नॉट ट्रू. बट बोथ द केसेस आर व्हॅलिड बाय फर्स्ट लॉ. सो फर्स्ट लॉ फेल्स टू टेल यू whether the process is possible or not. It checks only conservation of energy. Okay. Now we'll take third example here. Third example is a case of Pelton wheel. Here we have a closed system. म्हणजे कुठं आहे दाखवतो तुम्हाला. ही आहे closed system. Okay, this square box is closed system. Inside there is a fluid. Okay. आता मी काय केलंय, इथं व्हील अटॅच केलंय, व्हीलचा शाफ्ट आहे, शाफ्ट इथं तुम्ही माउंट केला आहे आणि त्याला एक दोरी बांधून त्याला एक वेट अटॅच केलं. आता काय होईल फर्स्ट केस मध्ये, जसं वेट खाली जाईल, as the weight will go down, this shaft will also rotate. As the shaft will rotate, this wheel will rotate. It will steer the fluid inside of the system and थोड़ा heat transfer देखील होईल. It will steer the fluid as well as there will be some heat transfer due to friction between solid and fluid. आता कॉन्व्हर्स पॉसिबल आहे का? ही सगळी हीट मी परत व्हीलला देणार, व्हील रिव्हर्स मध्ये रोटेट होणार, परत हे वेट वर जाणार. सो इट इज नॉट पॉसिबल इन रिअल लाईफ. बट फर्स्ट लॉ से दॅट इट इज पॉसिबल. कारण मला फक्त बघायचं की एनर्जी कॉन्झर्व झाली की नाही. फर्स्ट लॉला काही देणं घेणं नाही की ती प्रोसेस पॉसिबल आहे का किंवा रिव्हर्स होऊ शकते का, नाही. फर्स्ट लॉ ओनली चेक्स फॉर द कॉन्झर्वेशन ऑफ एनर्जी. ओके. So Converse is not true in the paddle wheel also. Still, first law of thermodynamics is satisfied. So from these day-to-day examples, it can be clearly stated that satisfying first law does not ensure for a process to occur actually. खरंच ती process होऊ शकते का? हे first law तुम्हाला सांगू शकणार नाही. So that is the limitation of first law. Process proceed in certain direction, but may not in reverse direction. First law thermodynamics has no restriction on the direction of process to occur. This hidden accuracy of first law to predict whether the process can occur is solved by introduction of the second law of thermodynamics. This inadequacy of first law to predict whether the process can occur is solved by introduction of the second law. Okay. तर मी तुम्हाला फार शॉर्ट मध्ये सांगेल काय होतं इथं. The very फार क्लासिक मशीन्स आहेत मी तुम्हाला सांगेन आता. फर्स्ट वन इज perpetual motion machine of first kind. Perpetual motion machine of first kind. ही काय म्हणते, ही एक मशीन आहे which will continuously do the work without any heat transfer. So perpetual motion machine of first kind is the machine which will continuously do the work without any heat input. First law काय म्हणते की perpetual motion machine is not possible because there is no conservation of energy. ठीक है? Because there is no conservation of energy. So first law काय म्हणते? First law suggests you PMM SK, perpetual motion machine of second kind. ती कशी आहे? ती एक मशीन आहे. अगेन त्या केस मध्ये there will be a heat input and all the heat is converted into work output. Okay. Now this is valid by first law. Well, first law says that this machine is valid. All the heat energy is converted into work energy. But in actual it is not possible. Always and always there will be some heat loss to the surrounding. This will be heat QH and QH. So PMMSK, so second law says that PMMSK is not possible. Okay, so write this down. Very important. PMMFK ही अशी मशीन आहे की जी फक्त कंटिन्युअसली वर्क करते, त्याला एनर्जी इनपुट नाही दिलं तरी चालतो. ठीक आहे. फर्स्ट लॉ म्हणते इट इज नॉट पॉसिबल बिकॉज देयर शुड बी सम कन्वर्जन ऑफ एनर्जी. सो फर्स्ट लॉ सजेस्ट यू PMMSK, perpetual motion machine of second kind. But second law thermodynamics काय म्हणते, हे पण होऊ शकत नाही. All the conversion of energy into work is not possible. That means no machine can have 100% efficiency. So there should be some heat loss to the surrounding. All this we'll study step by step. Significant. Second law of thermodynamics is not just limited to identity of the direction of the process. फक्त ती प्रोसेसचे डायरेक्शन सांगतो असं काही नाही. It also asserts that energy has quantity as well as quality. So this is again another concept is there, availability. That means out of available work, how much is actually we can utilize. So that also will be told by second law. It helps to determine the degree of degradation of energy during the process. How fast the energy is being utilized, that also can be told. It also used to determine the theoretical limits for the performance of commonly used engineering systems such as heat engine, refrigerators, etc. etc. आता तुम्ही असं नाही की बसलाय आता मला एक हीट इंजिन तयार करायचं आहे, आयसी इंजिन तयार करायचं आहे, त्याला काहीतरी लिमिटेशन्स आहेत. सो देर आर सम लिमिटेशन्स ऑन मेटलर्जिकल लिमिटेशन्स आर देर आर सम ऑपरेटिंग लिमिटेशन्स आर देर. असं नाही की तुम्ही एकदम 2000 केल्विनचं टेम्परेचर तिथं अचीव्ह करणार nahi. So there are some limitations for that engine. So all these limitations like higher temperature, lower temperature, heat transfer, total work done, All this is controlled by second law of thermodynamics. So before going to the actual law, so there are two laws in second law, that is first is Kelvin-Plank statement, another is Clausius statement. So before going to that, first we'll study some of the terms used in second law. First one is thermal reservoir, thermal energy reservoir. Second is source and sink. Third is the engine or the refrigerator, right? So basic terms first we'll study. In that first we'll study thermal energy reservoirs. Okay. तर काय असतं थर्मल एनर्जी रिझर्व्हायर्स? सो वी कॅन टेक एक्झाम्पल ऑफ ऍटमॉस्फेरिक एअर. आपल्या आजूबाजूला जी एअर आहे, आता त्यात मी किती जरी हीट ट्रान्सफर केली, एक समजा मी 1 मेगावॅटची एनर्जी त्यात ट्रान्सफर केली, किंवा त्यातनं किती जरी एनर्जी मी काढून घेतली, सपोज मी अगेन आय टूक 1 मेगावॅट एनर्जी फ्रॉम द एअर, त्याच्या टोटल एनर्जी कंटेंट मध्ये जास्त काही फरक पडत नाही. ठीक आहे, म्हणजे एअर तुम्ही बघा कुठून कुठून आहे, टोटल ऍटमॉस्फेरिक एअर ऑफ द अर्थ, त्याच्यावर फार फार म्हणजे फार बारीक इम्पॅक्ट पडेल, बट टोटल एनर्जी कंटेंट त्या केसमध्ये अप्रॉक्सिमेटली सेमच राहील. दुसरी केस आहे सन, राईट? सूर्याकडनं आपण एनर्जी घेतो. इन दॅट केस सूर्याला तुम्ही किती पण एनर्जी द्या किंवा त्याच्याकडून किती पण एनर्जी घ्या, त्याच्या टोटल कंटेंट मध्ये जास्त फरक पडत नाही. सो दॅट इज अ थर्मल एनर्जी रिझर्व्हायर. अनदर व्हेरी गुड एक्झाम्पल इज ओशन्स. आता ओशन्स मध्ये अगेन तुम्ही किती पण एनर्जी ट्रान्सफर करा, त्यातून किती पण एनर्जी काढून घ्या, त्या टोटल एनर्जी कंटेंट वर जास्त इम्पॅक्ट पडत नाही. सो दॅट इज ऑल्सो वन ऑफ द थर्मल एनर्जी रिझर्व्हायर. ओके, सो इट इज अ hypothetical body with relatively very large thermal energy capacity that can supply or absorb finite amount of heat without undergoing change in temperature. So there is no change in temperature. You supply X amount of energy, you absorb or extract the X amount of energy, there will be no change in its temperature. So for example, ocean, lake, atmosphere, two-phase system, industrial furnaces, etc., etc. Industrial furnaces, yes, there will be some increase and decrease in temperature, but mostly we are assuming they matter constant temperature systems. Now there are two terms, source and sink. So the thermal energy reservoir that supplies energy in the form of heat is known as source, and second is the reservoir that absorbs energy in the form of heat is known as sink. So always remember source and sink. Between source and sink you will have heat engine or refrigerator or heat pump. Now this is very classic case. So see here, there is again one paddle wheel is there, right? There is a shaft of paddle wheel is there. It is rotating. At the bottom, it has plates on that paddle wheel. Now, in this case, what will happen? We will supply or the heat to the fluid. So now the shaft will rotate. It will have some work. So like we are applying some work on the shaft. Shaft will rotate. Now it will rotate inside the water. All the work here, it will be converted into heat. So this is a classic case of paddle wheel mechanism. But inverse or the converse is not true. We cannot supply to the heat to the water and this shaft will automatically will rotate. असं actual मध्ये होऊ शकत नाही, right? तुम्ही shaft rotate करा, त्याच्यातनं heat transfer होईल, it is understood. But तुम्ही heat transfer करा आणि shaft rotate होईल, it is not possible. So from such examples, it can be concluded that work can be converted into heat, but converting heat to the work requires special devices, and these special devices are called as heat engines. So before going to the actual heat engines, we'll see what are the characteristics of the heat engines. They receive the heat from very high temperature reservoirs. Okay, that is source. For example, solar energy, oil furnace, nuclear reactor, etc., etc. They convert part of this heat into work. So that is in the form of rotating shaft. They reject the remaining heat to the low temperature reservoir, that is C. So you can take example of nuclear reactor. आता तुम्ही बघितलं असेल, most of the nuclear reactor हे किनाऱ्यावर असतात, very nearer to the ocean. Okay, का असं? Because in case any explosion or any calamities happen, so there will be no disaster on mass level, so that all the damage can be controlled at that site only. But another thing is here it is, they have very large amount of sink, that is ocean. But त्या केस मध्ये source काय असणार आहे? Nuclear reactor will be source which will supply the heat. All the heat or some of the part of the heat is converted into work, and the remaining part, heat loss, it is supplied to the sink, and here sink is ocean. म्हणून न्यूक्लिअर रिएक्टर हे आतापर्यंत सगळ्यात इफिशियंट पॉवर जनरेटिंग सिस्टीम आहेत. तुम्ही जर कम्पेअर केलं हायड्रो पॉवर, थर्मल पॉवर और रिन्युएबल एनर्जी लाईक सोलार, विंड एक्सेट्रा, सगळ्यात आतापर्यंत इफिशियंट आहे न्यूक्लिअर रिएक्टर्स. त्यामध्ये जास्तीत जास्त तुम्हाला इफिशियन्सी मिळते. They operate on a cycle. Heat engines are generally work producing devices. So these terms will come again and again. Turbines. So turbines is the example of heat engines. So heat engines are work producing, and refrigerator and heat pump are work consuming devices. So this is a very classic diagram for the heat engine. Please draw it, because time again and again this diagram will come. So in this case, here we have source, high temperature source, we have low temperature sink, in between you have a heat engine. So what heat engine will do? It will take the heat, it will convert some amount into work, and it will reject some heat to the sink. So this is a schematic diagram of the heat engine. For example, you can take IC engine. In IC engine, you receive the energy in engine through combustion. Heat engine is engine itself. Okay, so I'll correct myself. You will receive the heat in the cylinder during combustion. Then engine acts as a heat engine. Some part is converted into shaft work, right? So here we have crankshaft, it rotates. So that is a work output. And some amount of energy is lost in the exhaust gases or the transfer to the walls of the heat engine, right? So that is a loss of energy. If you take example of thermal power plants, in that case, boiler is where we receive heat, turbines act as the heat engine, and condensers act as a sink. Okay, I hope everybody has drawn this diagram. This diagram is very important. Okay. So the theme of this subject, applied thermodynamics, is here on your screen. It is related to one of the major applications of thermodynamics, that is steam power plant. So it is an example of an heat engine, and it is an example of a cycle also. So in this case, heat engine is turbine. It will receive its heat at boiler. In boiler, what we do, we supply coal, right? So the burning of coal takes place, it gives up heat. In the boiler also we have water jackets or water tubes. So these water tubes absorb the heat coming out from the coal. It will get converted into high pressure steams. Now this high pressure steam will fall on the blades of the turbine. The shaft of the turbine will rotate. It is connected to the shaft of the generator. In generator, electricity is generated. That is our work output. Now some amount of heat is lost in the form of low pressure steam. म्हणजे काय होतं, high pressure steam ची energy utilize होते, and outlet is low pressure steam. So this low pressure steam passes through tubes and it is passed to the condenser. In condenser, as the name suggests, condensation takes place. Steam is converted into water. This water is pumped with the help of the pump. So here the pressure difference is there. So boiler pressure is very high, condenser pressure is very low. In order to raise the pressure of water to the boiler pressure. So we are using pump. So these are the main components of the thermal power plant. So draw this diagram. This diagram is very important. Here source will be the boiler in the furnace, sink will be the condenser, heat engine will be the turbine. Okay. And if you consider the whole thermal power plant station, it will be a cycle. This is a cycle. This is a closed cycle. Okay. Again, this water will be boiled into steam. This steam will come into condensation. It will convert to water. Water will be pumped. Again, this water will supply to boiler. This way, this cycle will repeat. Obviously, there will be some loss of water during the boiling process. So there will be some makeup water is provided in the actual power plant. So if you see the actual power plant, it is very different. There are 1,000 number of equipments added to these major components. If you get a chance, we can arrange industrial visit. So 2 years before, so the students who are in this final year of mechanical engineering, they got a chance or opportunity to visit a nuclear power station at Tarapur, right? So through our references, we received permission to visit that power plant. Students went there. They got the opportunity to see the actual nuclear power plant of Tarapur. They got to see all the components which are contributing for the power generation, right? So if we also get a chance, if this situation, Corona situation becomes better, we can also arrange one industrial visit to such power plants. So when I was studying, at that time, I got an opportunity to study a power plant, Nagarjuna power plant in the Andhra Pradesh at that time. So that was actually a hydropower plant. Through your reference also, if you get a chance, so in Maharashtra, the major hydropower plant is Koyna's hydropower plant. Thermal power plant we have in Solapur, and that also we can see the components. If you want to see nuclear power plant, we have two nuclear power plants. One is at Karwar at Karnataka border, and one is at Tarapur. Also, in my college days, I got the opportunity to see the nuclear power plant of Karwar. So in our second year of engineering, college has arranged one industrial trip to the Karwar. In Karwar, we got to see both nuclear power plant as well as hydropower plant. In my third year of engineering, again for the power plant engineering subject, we went to this Nagarjuna hydropower station at Andhra Pradesh. So like that way, if you also get a chance or if you're interested, we can arrange such trips. So depending on the situation of Corona, the permission, whether we'll get a permission or not, that will be decided. So this is an example of a heat engine. Can Q out be eliminated? Q out is heat loss to the surrounding. Can it be eliminated? If we decrease the Q out, obviously our efficiency will increase. Answer no. Without a heat rejection process, the cycle cannot be completed. And this is the statement by second law of thermodynamics. Without a heat rejection, the cycle cannot be completed. So net work output here, it will be work out minus work in. Here this work out refers to turbine work. Work in refers to work required to drive the pump. Okay. Again, very important question. I ask my students oftenly, what is the difference between pump and compressor? What is the difference between pump and compressor? So you can also try your luck. If you know the answer, you can type in the chat box. Yes, what is the difference between pump and compressor? Why we are not using compressor here? Why we are using pump here? As diploma people, if you know the answer, you can type in the chat box. Pressure difference. No. What question I am asked is, what is the difference between pump and compressor? Where we use pump and where we use compressor? Why we are not using compressor in this case? Okay. So it is a actually expected response. Many of the students don't know. So what is the difference between pump and compressor? So one more response is there. Pump used for high pressure. Okay. So same answer, similar answer is given by Prasad. Shivraj also has given the same answer, pressure difference. So it is not related to pressure difference. It is related to type of fluid used. Okay. Both are used for the fluids, but the compressor is preferred for the gases and pump is preferred for the liquids. Whenever we have liquid, we go for pump. Whenever we have gases like steam, we go with compressor. Okay. So here at the end of condenser, we have water. So that is why we are using pump. As simple as it is. It has nothing to do with the pressures. If it has a steam or gas, in that case, we are using compressor. Okay. For the pressure purpose, again, it has some types. In pump also, we have say various types. So for depending on the pressure application, we have different types of pumps. Depending on pressure application, we have different types of compressors, right? But the main difference between pump and compressor is the type of fluid use. If you are using for gases, we are using compressor. If you are using for liquids, we are using pumps. Now here work output is work out minus work in. Work out is turbine work, work in is pump work. Each component is an open system, but however, a complete set of components, no mass flows in or out of the system. Hence, can be treated as closed system. And in closed system, the change in internal energy is zero. Okay, total energy in the system is conserved. That is why change in internal energy is zero. And net work output will be equal to Q out minus Q in. So write down this. These are the two formulas for the workout. Workout can be turbine work minus pump work, or it can be Q out minus Q in. Whatever heat received by the boiler and heat lost to the condenser, the difference is net work output. Now from this we can easily calculate the efficiency. So the part of heat output is converted into work output, is measure of performance of the heat engine. It is known as thermal efficiency of the heat engine. Okay. So thermal efficiency, here it is net work output divided by total heat input. What is net or what output? Turbine work minus pump work divided by the heat received by the boiler. Whatever heat is received in the boiler, that will be at denominator. Total work done, that is turbine work minus pump work, that will be numerator. So write down this formula. Thermal efficiency will be equal to okay. So here is the formula. Very small is there. It is not visible, but still it is NTH. So this is a symbol for efficiency. NTH W net divided by QA, or we can write it as a W net. I can write it as a QH minus QL. So I write it down here with the help of annotations. So thermal efficiency is given by this symbol NTH. Okay. So this is equal to W net divided by Q in. Okay. Now we know that W net is equal to Q in minus Q out. So I'll write it down here. So NTH will be equal to Q in minus Q out divided by Q in. So this can be written as, I hope you know this, how to write this. This will be equal to Q in divided by Q in minus Q out divided by Q. And this can be reduced to 1 minus Q out divided by Q in. Okay, this formula is applicable to all the heat engines. You can apply this formula for the IC engine also. You can apply this formula for the steam power plant also. So everywhere you can apply this formula of thermal efficiency. So write down NTH is equal to W net upon Q in, or 1 minus Q out divided by Q in. Okay. Here QH or QN is the magnet of heat transfer between cyclic device and source of temperature, that is TH. QL or Q out is the magnitude of heat transfer between cyclic device and seek temperature TL. So work output in other terms QH minus QL or thermal efficiency will be equal to 1 minus QL by QL. So generally we will be using QH and QL. We won't be using Q in, Q out. We will be using QH and QL. Okay. So always there will be a one diagram. I will draw here. There will be a source will be there, which is at temperature TH. So always remember TH is the temperature of source. Then it is connected to a heat engine. This is the symbol of heat engine. Okay. Heat engine will receive QH amount of heat. QH is heat received from the source. Next, we have it will do some work, that is W, and it will release some amount of heat, that is QL. So QL is heat lost to sink. Now sink is at temperature TL. Okay, TL is the sink temperature. So always remember this diagram: TH, TL, QH, QL, and W. So heat engines must give away some heat to the low temperature reservoir, that is sink, to complete the cycle. Thus, a heat engine must exchange heat with at least 2 reservoirs for continuous operation. And this forms the basics for the Kelvin-Plank statement. Okay. So what is it? How it works? We'll see in next lecture. Okay. I hope for today it is sufficient. Okay. Or shall we continue? What do you say? Shall we continue? Okay. So I'll just tell you what is Kelvin-Planck statement, what is Clausius statement. So Kelvin-Planck statement. Okay. So we started with PMM-FK, which is a machine which do only work without any heat input. So first law says that PMM-FK is not possible. There should be an energy conversion. First law suggests you PMM-SK, a perpetual motion machine of second kind, in which it receives heat, it converts all heat into work. Okay. But second law says it is not possible. No machine can have 100% efficiency. So this is stated by this Kelvin-Planck statement. So whenever you are referring to second law, there are two statements: Kelvin-Planck statement and Clausius statement. Okay. So what is it? We'll see. So it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce net amount of work. That means you cannot convert all the heat input to all the work output. So there is a diagram here. So see here, there is another power plant is here. This is a power plant. This is our, we call it as a heat engine. It receives heat in the boiler, 100 kilowatt, and it converts all amount of heat into work, that is 100 kilowatt. 100 kilowatt heat is converted to 100 kilowatt of work, and there is no heat loss. And Kelvin-Planck statement says that it is impossible. It is as simple as it is. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce net amount of work. You cannot convert all the heat into all the work. Alternatively, no heat engine can have thermal efficiency of 100%. How? So the formula for thermal efficiency we have seen is equal to W divided by QH. Now in this case, QH is equal to W. So net efficiency will be equal to W, say upon W is equal to 1. Or we can say it is 100% efficient. Kelvin-Planck statement that this is not possible. Okay. Okay. So I'll take a recap whatever we have learned today. Then we can stop. In next lecture, we'll take a recap whatever we have learned, and then we'll see what is a Clausius statement. Because to understand the Clausius statement, you need to study first the refrigerator or heat pump cycles. Okay. So let us take a quick recap of whatever we have learned today. So obviously we started with numericals, 1 hour we had given for the numericals of the first law. Then we started with the limitations of the first law. So in this case, first law is concerned only about conservation of energy. It is not concerned, or it does not give you guidance about the direction of the process. Okay. Again, first law does not talks about quality of the energy. So for this, we have second law. Second law gives you direction of process. Also, it gives you quality of the work that can be produced. So here we saw two terms, thermal energy reservoir, that we have seen two terms, source and sink. Then we have seen the heat engine diagram, right? Then we have seen the example of power plant, thermal power plant as an example of heat engine. Then we have seen the formula for thermal efficiency, that is 1 minus QL by QH, or W net divided by QH. Then we have seen Kelvin-Planck statement. Kelvin-Planck statement states that no heat engine can have 100% efficiency. Okay. In next few lectures, we'll study Kelvin-Planck statement, and then we'll start the concept of entropy, because concept of entropy is very important, not only thermal point of view, because entropy is concept is very applicable to philosophy also, in day-to-day examples also. So that we'll study. So in next lecture, what we'll do, we'll cover the Clausius statement, we'll solve the second law numericals. Okay. Okay. So with this, we'll stop today. Put your attendance in the chat box. Enter only numbers. Don't enter SB, anything. Just type your roll numbers. Yes, others, enter your roll number in the chat box. So before your IC first comes, we will finish the first two chapters. First chapter itself is a task, big task, because I want to make sure that you are understanding the basic concept, because these will be required in subsequent chapters. So first chapter always takes time, but we'll go slowly. If you are understanding very good, if you are not understanding some part, you can ask me anytime. So I hope everybody has put their attendance. Now with this, we'll stop today. Thank you for attending.